is that you cannot measure energy directly. Remember, energy, much like wind, isn't something that you can actually like get your hands on. You can't catch it in a jar and put it on a scale or something like that. So what you have to do is measure actually how energy is changing something else. Usually temperature, right? Like everybody knows, if I take energy and add it to a cup of water, the cup of water's temperature is going to increase, right? So we can measure that change in temperature and convert it over to a value of energy. Now, there are two variables that affect how much energy is needed to change temperature. Those two variables are mass and identity, right? So let's just talk about this idea for a second. Let's say you're going to make yourself a quarantine snack, right? And you have soup to choose between and nachos. So if you want the fastest possible snack, you're going to want to fix the thing that will warm up the fastest, right? Well, soup takes like 4 or 5 minutes to warm up because it's made of mostly water, whereas you can have a piping hot plate of nachos in like 30 seconds, right? Because they're mostly made of corn or some other solid. And the reason for that is that soup and nachos have different specific heats. In other words, it takes different amounts of energy to change their temperature. Okay. The other thing that affects how much energy it takes to change the temperature is the amount of the substance that's present. And I think you guys all know this, right? For example, if I want to heat up a cup of water, it takes, a couple of minutes. Whereas if I need to heat up a bathtub of water, like boil a bathtub full of water, that's going to take a lot longer. So the amount of the substance also affects how much energy is required to change the temperature. Okay. Now, one real quick little idea that I want to point out here. So far, we've been representing energy with an H, which stands for enthalpy. Now we're going to switch gears and we're going to represent energy with a Q. And I'm not really sure why. I should probably go back and read the history of why we did that. So they both represent energy. The difference between the two comes from the unit. So the unit for delta H is kilojoules, right? Like the kilo prefix, whereas the unit for Q, for that energy that is needed to change temperature, is in just regular joules. So just like grams versus kilograms, this is joules versus kilojoules, okay? The other thing that I want to just point out really quick before we try a practice problem is the equation. So to find out the amount of energy that's needed to change the temperature, you have to know how much the temperature changes, right? So you're going to take the final temperature minus the initial temperature. You're going to multiply that by the specific heat. This is a value or a constant that will be always given to you. And then, of course, the mass, multiply by the mass, okay? So you plug all those numbers and you get a value for Q. If the number is positive, then that means that you have to put that much energy into the system or whatever you're looking at in order to get the temperature change. If the temperature is negative, then it means that energy has to be released to experience that temperature change. And it's everybody's favorite just plug and chug method, right? You read your problem, you plug your numbers in, and then you use algebra to solve. Okay, so let's look at a couple of examples. You guys, of course, had some practice problems to do over this and then a lab, and then there are 3 problems on the review. So we're going to check out a couple of them right now. So it says how much heat, so remember we're going to represent heat with a Q, is required to raise the temperature of 8 grams of water, so that right there is my mass, by 3 degrees Celsius. So we're changing the temperature by 3 degrees Celsius, okay? So we're going to take that equation, Q is equal to mass times specific heat times the change in temperature, and we're going to plug in our numbers. We're looking for Q, so I'm going to leave that as a Q. The mass is 8 grams. Now, we're dealing in water here, so we would need to look up the specific heat of water. I happen to have it off the top of my head. It's 4.184, but you could look it up in your own problems. I will give it to you on the test, unless, of course, I'm asking you to solve for it. And then we're going to multiply by the change in temperature. In this case, the change in temperature is already given to us. It's 3. So we just have to take grams times the specific heat times 3. 8 times 4.104. Oh, wait, sorry. 8 times 4.184 times 3. And we get 100.42, and the unit, of course, will be joules. So that's how much energy would have to be applied to 8 grams of water in order to get the temperature to change by 3 degrees Celsius. Okay, pretty straightforward. All right, let's look at this second problem here. I have 22 grams of metal that is going to absorb 713 joules when it's heated from 28.3 degrees Celsius to 72.8 degrees Celsius. What is the specific heat of the metal? So I'm looking for specific heat this time, right? My mass is 22 grams, so there's my mass, right? And the energy involved is 713 joules, so that's my Q. And then here I can find my change in temperature, okay? So again, I'm going to use that same equation. Q is equal to mass. And you, of course, don't need to write that out, but I am just for learning purposes, times the specific heat times my change in temperature. And actually, you know what? I'm going to change this. I'm going to put, for my change in temperature, I'm going to put the actual values that I need to put there. So I'm going to do final temp minus initial temp. Okay. All right, so let's just plug and chug through this problem. So Q is equal to 713, right? Mass is 22 grams. The specific heat is what we're looking for, so I'm going to just leave specific heat symbol there, so I know that that's what I'm trying to solve for. I'll put a little box around it. Times the change in temperature. So the final temperature was 72.8, and the initial temperature was 28.3. Okay, so I'm going to take care of that temperature change really quick first. So 72.8 minus 28.3, and I get 44.5. Okay, so I'm going to cross that out, and that's my value for that number. So I just have to get specific heat by itself. So there's numbers over here on this side with a specific heat. So how do I solve for specific heat? Well, I need to get it alone, right? And so right now I'm multiplying by these numbers. If I want to get rid of them to get specific heat, what do I have to do? I need to divide. So I'm going to write here again so that you know what you're doing, that you're going to divide by 22 and divide by 44.5. Okay, that will eliminate those values from this side and it'll have specific heat all alone. But remember that math is fair. So if I divide by those two numbers on this side, then I also need to do it over here on that side. Okay, so I'm going to take 713 and I'm going to divide by 22 and divide by 44.5, which happens to be 979, right? So I'm going to take 713 divided by 979, and I come up with a specific heat of 0.73. Now, this has some crazy units. I'm not necessarily worried about you knowing the units. The unit is joules per gram degrees Celsius, because what specific heat tells us is the amount of energy needed to raise the temperature of 1 gram of a material 1 degree Celsius. Okay, so don't worry too much about the unit, but that is what it is. All right, and then final problem, you will have one problem just like this on the test, and the reason you'll have a problem just like this on the test is because it's exactly like the lab. Okay, here's what you need to understand about energy transfer. Is that energy is transferred between two substances until they reach the same temperature. So when I take a hot liquid and I pour it into a cold liquid, the two things mix together until they reach the same temperature. The same thing happened in our lab. We took a hot metal and put it into a cold water, and the two exchanged energy, or energy was transferred from the hot metal into the cold water until a final temperature, like when it hit equilibrium and stopped changing, was met. Okay, so because of that, we can set those energy values equal to each other. In theory, it should be a perfect transfer of one to the other. Now, in reality, energy is lost to the container and the environment and all that fun stuff, but we're not going to worry about that. Okay, so what we can say is that the energy of the water in this situation is equal to the negative energy of the metal. And the reason that has a negative value is because the metal is going to lose energy, right? Water has a positive value because it's going to gain energy. So if we take this equation and then plug in what we know about Q, we get a giant equation that says that the mass of water times the specific heat of water times the change in temperature of water is equal to, and again, that negative is really important, the negative mass of the metal, right? Does it tell us the identity in this problem? No, I'll just put metal. Mass of the metal times the specific heat. Sorry, I'm like going off the edge of my table over here. Specific heat of the metal times the change in temperature of the metal. Okay? So all I need to do is plug in the values that I have and solve for whatever is missing. So let's read this problem here and see what we're going to try to solve for. It says that a piece of metal weighing 59.047 grams, so metal is 59.047 grams, that's going to go over here. Here, I'll just write it as we go. Was heated to 100 degrees Celsius. So that would be my initial temperature of my water, right? Or I'm sorry, the initial temperature of my metal. So that's 100. So I'm going to put that there. And then put into 100 milliliters of water. We haven't really discussed this too much, but 100 milliliters is the same thing as 100 grams because density has a value. Density of water is 1 gram per milliliter. So my mass of my water is 100 grams over here. And its initial temperature was 23.7. So again, that goes there, right? Okay, we know the specific heat of water, of course, is 4.184. Okay, now the metal and water were allowed to come to an equilibrium temperature determined to be 27.8. In other words, the final temperature that the two things met that came together was 27.8. So our final temperature is 27.8 and 27.8. Okay, it says assuming no heat is lost to the environment, which is impossible, calculate the specific heat of the metal. So what we are looking for here is that specific heat of the metal. Sorry. Okay, so I'm just going to leave that in as my variable and then put a box around it so I remember that that is what I am trying to solve for. Okay, so these two values are equal to each other. Again, this is just a matter of plug and chug, right? We put all these numbers into our calculator and then we are left with an equation to solve. Okay, so let's do that real quick here. So 100 times 4.184 times the change in temperature, which again, you need to make sure you're good with your parentheses so that you don't mess that part up, is 1,715.44. And that is equal to the information about the metal. And again, remember, we have to watch out for that negative value. So I can take these two sets of numbers and multiply them together. So let's see here, 27.8 minus 100 times 59.047 gets me a negative 4263.19, and of course times the specific heat. That's what we're looking for. Okay, so now I just have to solve for specific heat. Real quick, let's take care of this double negative situation. Do you know what you do whenever you have a -1 minus or times a negative? You multiply, right? Or I'm sorry, you make it positive. So that just makes that positive. Okay, so the double negative becomes positive. Maybe we'll put that here so that you remember. Double negative becomes positive. Okay. And then again, to get the specific heat alone, we just have to divide by that value. So we're going to divide by the 4263.19. And then we're also, since again, math is fair, if we divide by 4,200 on this side, we also have to divide by the 4,200 on this side. Okay, so that crosses that out, and I'm left with my specific heat. So
So specific heat is equal to 1715.44 divided by 426.3.